Indeed, it's organized with together with FCAI and HiDATA. So FCAI is the Finnish Center for Artificial Intelligence, which is a community of experts in artificial intelligence in Finland. And it has been initiated by Aalto University, University of Helsinki, and VTT Technical Center of Finland. And FCAI is also one of the Academy of Finland flagships. HiDATA is there to solve data challenges, and it's a center in large or multidisciplinary network of researchers working on both methods and applications supported by data science infrastructures. And it's joint hub of University of Helsinki and Aalto University. And please note that we are recording this session. And indeed, so we will have 2 talks, and then you will have some opportunities for asking questions indeed. So please note that we will be recording it in that moment. But indeed, I'm your host today. So my name is Simo Sarkka. I'm an associate professor in Central Informatics and Medical Technology area and with Department of Electrical Engineering and Automation in Aalto University. And I'm also the leader of AI across fields in FCAI, and also a fellow of ELLIS, which is the European Lab for Learning and Intelligence Systems. And today's program is that first we have Otto Seiskari giving a talk on BLA and its alternatives for contact tracing from the point of view of indoor positioning. And then we have a small amount of time for questions and discussion. And after that, Alexander Thurroth will give a talk about sharing light on the network of the FCAI AI task force. And then we have some more time for questions. And indeed, for questions, we will have the questions after the talks, and you can use either, you can raise your hand or use the chat to write the questions over there. But indeed, we can go to the first talk, which is by Otto Seiskari. So he's a Doctor of Science in Technology and also CTO in IndoorAtlas, which is a company providing sensor fusion-based indoor location services to billions of mobile devices around the world. His background is in mathematics, data science, software engineering, startups, and also he also used to, he is a co-founder and used to work with Kaiku Health before. But anyway, his talk is about PLA and its alternatives for contact tracing from the point of view of indoor positioning. So please, I will let you share your screen. Okay.
Okay, just a second. So I think my screen is now visible.
By the way, we are not recording right now. Should we be?
Okay, I'll actually stop the video, I think.
Okay, yes, now we are.
Okay, so you can see my screen now, I think.
Yes, it's good.
Okay, great. I'm Otto Seiskari. I represent a company called IndoorAtlas, which I'll present here really quickly so that we can get to the main topic of today. And what we do is that we provide indoor positioning services. We operate in multiple different regions, and technology is based on sensor fusion or technology fusion, so that we try to read everything we can out of the mobile phone and provide the best possible location. And the main product is an SDK, which is a piece of software that is integrated into our customers' applications. So we don't usually make applications, but our customers do. And our SDK provides them with the indoor location capability. So the biggest customer by number of users is Yahoo Japan, who are a Japanese map application provider, among other things. And if you open their map application in one of the large metro stations in Tokyo, then it uses our technology to provide the indoor location inside these large venues. And how the process works, so this is the basic idea. So it begins with what we call mapping or fingerprinting, which is also sometimes called a signal survey, so which corresponds to the data collection phase in machine learning terminology. So how it works is that somebody goes into the venue where we want to enable indoor positioning and walks, kind of covers the whole venue, all the areas in which positioning is supposed to be working, and records data with the mobile phone, and from time to time indicates their true location. And then this data is uploaded to the cloud, where we do the training phase in machine learning terminology, and the output, the models that come out are called signal maps in this context. And how the actual positioning works is that the devices that want to position themselves download these compressed models, and then use these to kind of match against the signal data that they record and compute their position. So this works offline in the sense that the data doesn't need to be uploaded to the cloud by the end users for this to work. And the techniques that we used, so here are the most important ones. The first one is radio positioning, which I'll describe in more detail in just a minute. Then we also use, it provides you your kind of rough location. Then we also use PDR, or inertial navigation, which means tracking the relative movement of the phone based on the IMU, the inertial sensors. The barometer is also available in some phones, and it's really useful for tracking changes in floor number, so changes in the Z coordinates. And then our specialty is called magnetic terrain matching, which means that we actually produce maps of the geomagnetic anomalies in the building, and we can use these to help and stabilize the positioning. And this slides will be shared later, so you can for example open this link and check out this video of how this works. But in this presentation, I'll concentrate on other things. So here's a quick demo of how this could look like in practice. So here on the, I hope you see this video, but on the so here in the beginning you see that the location accuracy was not super good. I'll just rewind so you can then again. So we start with radio positioning that provides you with an approximate location, about 10 to 20 meters accuracy. But then the longer the user walks while the application is active, either in the background or foreground, the more accurate the location becomes, because all the other technologies start to, in a way, kick in. And then we achieve this tracking accuracy of about 1 to 2 meters after convergence. Okay, but today I'll talk a bit more in detail about this one of these components, radio positioning, which is used to which we use to get the kind of rough initial location for the other technologies, among other things. So the most basic version of radio positioning would look like this. So first we have the signal map, which is called a Wi-Fi map in this case. The most basic version could be just a list of Wi-Fi access points together with their geographic locations. Then when a device wants to position themselves, they observe a so-called Wi-Fi scan, which contains a list of these Wi-Fi identifiers called BSSIDs together with the signal strength values. Then what you can do is you can map these signal strength values distances, and then with this information you can quote unquote trilaterate your position. So this is not what we kind of really do in the actual models, but anyway, this kind of gives the correct intuition. And here's a picture of an kind of actual Wi-Fi map from one of our signal surveys. So just to give you an idea how many access points there usually are in urban areas, so quite a lot. And so this kind of gives a good intuition why this is such a useful signal, like source of information. Okay, so this may sound exotic, but this is actually the method your phone, when you open any map or other location-based application, what is actually most often used to compute your location. So when you use the built-in location services from Apple or Google, actually they have these Wi-Fi maps that are built using crowdsourcing methodologies. So for example, here's an Android screen that asks for your permission to do this and collect this data for building these maps. And these maps basically cover the whole world, excluding maybe some areas for political reasons. And this kind of Wi-Fi positioning, which is actually used when you think you're using GPS, so it's actually possible to make it quite battery efficient. So you can try this by just turning on the Google Maps location history or timeline feature, and as a result, an Android phone will track your location 24/7 in the background without draining your battery. So this is a kind of a common misconception about location data on GPS, so that it would drain your battery. So this is not really true. Okay, so what are the main kind of issues in using this for example, contact tracing or proximity detection? So the main issue in these crowdsourced maps by Apple and Google is that they're, especially their kind of altitude information or floor number information is not very accurate. So this is these are kind of proprietary methods. It's not public how they work, but kind of presume that this is because it's a lot harder to crowdsource these three-dimensional maps than two-dimensional maps. And as a result, you get usually rather good latitude and longitude information, but not very good altitude information. But this is a property of the crowdsourcing method. So with Wi-Fi positioning, it is possible to also quite easily get your floor number information or altitude information. For example, doing these indoor fingerprints, but also by, for example, directly comparing these Wi-Fi scan data from different devices. And all in all, you can the kind of accuracy you can expect from Wi-Fi positioning is around room level accuracy. Okay, but the main practical problem with Wi-Fi positioning is actually that it's about Apple policies. So they're actually blocking everybody else except themselves for using this Wi-Fi scan data on iOS. So they use it for their own indoor positioning business, but they're blocking others from using it. So for this reason, the kind of third parties must use these devices known as iBeacons, which are these kind of small battery-powered Bluetooth transmitters that you actually have to install in the venue that you want to enable positioning in. And as a result of this, we actually know quite a lot about this one particular problem that is in the core of both radio-based indoor positioning and Bluetooth contact tracing, which is the question of how to map this signal strength information to distance. And in theory, this should be really simple. So there's this thing from high school physics called the inverse square law that should tell you how the radio signal strength changes with distance. And the RSSIs that we measure are just a logarithmic scale for this thing. So it's rather easy to, so you can easily come up with this formula that should tell you how the transmission power of the device and the signal strength that you both know map to distance. But like many interesting formulas from high school physics, this is only guaranteed to work as is in a vacuum. And if we exit the vacuum, then things start to look quite noisy. So here's an actual measurement, and where it comes from is this kind of signal survey. So here the cyan dot is an iBeacon device. So it's a fixed Bluetooth transmitter. And then in our signal survey, we have measured the signal strength all around this one floor of this particular venue. And from this information, we can kind of plot the measured RSSI, the signal strength, against the known distance. And the red thing here shows the best fit of the inverse square law. And just to kind of elaborate, so this is not a bad or pathological case at all. This is a very typical case in how the data looks like. And one more comment about this is that it does not, so it helps to average these RSI values over time, but it doesn't really solve the issue, so that these kind of artifacts don't go away, and this due to an effect known as multipath propagation, so that the radio signals bounce around in the building and create these kind of unpredictable patterns of signal strength inside the building. And here's another kind of issue that you might encounter in this. So here's an example from our. So we actually kind of crowdsourced this from our production data. So this is two different phone models that are in the same environment over a long period of time, and they measure the distribution of these RSSI values. And here you can see that between Google Pixel 2 and Google Pixel 3, there's a 10 decibel difference between these mean received signal strength values, which means that if you don't calibrate for this effect, then you get a threefold multiplicative error in all distance measurements that you do using the formula showed above. And again, this is not a bad case. This is a typical case. So there has been up to 30 decibel discrepancies, which means 30 times multiplicative error. And in contact tracing, if you use, so here, this data is from a case where the transmitter is actually the same iBeacon or the same set of iBeacons, so it's exactly the same. But if you use different phones for transmitting these signals, then you also have a similar effect from the transmitter. So different phones, even if you tell them to transmit with the same power level, the actual power levels they transmit are quite different. And this is not the only source of variation that you have, and it's difficult to model. So for example, the direction you're facing, or in which pocket the phone is, or is it in a purse or a table, these all have very large effect on the RSSI, as well as the number of people around, so how crowded the space is. So to conclude, so to measure distances reasonably from these signal strength values, you actually have to calibrate your system for every possible phone model that you want to support. So this is fully doable, but it's quite a lot of work. But even after you do, there remains quite large unmodelable errors in the signal strength, and this may cause you like threefold multiplicative errors. So which means that if you measure, one phone would measure 1 meter, then the other would measure like 3 meters. And as a result, also for this Bluetooth-based proximity detection, the realistic accuracy is very similar to that of the Wi-Fi positioning. So it's also room level accuracy. There has been a previous discussion about in the public about defining some contact as exposure at 2 meters or 5 meters or something like that, but you cannot actually distinguish this between these based on this data. Okay, then the final part, which is the more controversial one, So okay. So first, let's go through the basic of this digital Bluetooth-based contact tracing systems. So there's different variants, and this what I'm mentioning here, this applies at least to the DP3T system or the Google, Apple exposure notification framework, and possibly also others like the PCN protocol and this PACT protocol. In any case, how it works is that other devices that participate in this this protocol, they broadcast these so-called temporary, so frequently changing cryptographic random identifiers that are known under different names, but it's the idea is the same. So this frequently change, and they are sent to other devices, and the phone also records all the IDs it receives from other devices. Then, if somebody reports themselves infected, so this is a voluntary thing. So if you've been tested positive and you want to announce it through the app, then the identifiers that your device has previously broadcast are published, and published in the sense that they are downloaded by all the other devices that participate into this system, and the other devices then check for matches. So for in this example, so if this device would have received of these devices and these have been reported infected, then it checks, finds a match in this local kind of history, and it kind of then deduces that, okay, so if all the RSSI proximity thresholds are met, it then deduces that, okay, the user has been infected and shows a warning notification. Okay, so why this has been selected or is endorsed instead of location data? So it's based on this, what I would call a value proposition, so that if this was all there is to this system, so that the only information the users would learn is if they have been in contact with another, with an infected individual or not, then this would be a lot more private than location data. But the issue is that this kind of value proposition has never been really tested. So this kind of and it's based on brand new decentralized cryptography. So this kind of let's say a new cryptographic protocol, like just invented 6 months ago, and now it's so not very widely tested, and this is kind of the core of this value proposition. And I'm going to next show some like a few possible issues with this, and some of these can be fixed or can be addressed with, let's say, more brand new cryptography. But I'd like to remind you that if any of you remember something about the blockchain and cryptocurrency incidents that happened a few years ago, then there's actually quite a lot of things that can go wrong if this new cryptographic decentralized stuff is deployed to kind of production without wider testing. And this, if you haven't read about this, for example, this Ethereum hard fork story, I strongly recommend it, because it's quite unbelievable stuff what went wrong there. Okay, so what are the things that can go wrong? So simply the fact that you're broadcasting these identifiers around you, they actually reveal instantly if you are using the app or not to anybody around you. And it's, for example, it's quite easy based on this to kind of discriminate against you if you're not using the app. So it's probably not legal, but you can do it quite easily, because your phone is constantly telling everyone around it that if you're using the app or not. And there's a bit more kind of serious attack. So this published as called the paparazzi attack. So now, if somebody kind of links your identifier, some of your temporary identifiers with your identity, for example, by placing a Bluetooth sniffer in a security camera, which snaps a photo when it observes one of these temporary identifiers, then they can later learn that you were the infected individual. And similarly, if they link these temporary identifiers with location data, then they can draw maps of the infected kind of areas, or areas in which the infected individuals have been to. So which are kind of the red. In this simulation, they would be the red dots in this map. So if somebody had installed Bluetooth sniffing hardware all over city centers, then they would learn kind of the traces of the infected individuals. And this is actually in the currently proposed protocols, such as the Google, Apple exposure notification framework. The type of exposed information is actually a bit worse, because to save kind of bandwidth, download size, they actually publish not only these infected individual IDs, but also so-called diagnosis keys that are something that has been used to generate these IDs, so that they link all the IDs, temporary IDs broadcast by the same person together. So this would be, in this example, this would be these lines connecting the dots. So potentially they actually expose the full kind of daily routes of the infected, including where they work and live, to any third party with enough Bluetooth sniffing hardware, or with enough installed applications with Bluetooth and location permission. So any mobile app with these pair of permissions can act as a Bluetooth sniffer and kind of leak this information to third parties. Okay, and then kind of based on this, I made this kind of alternative comparison of Bluetooth and location data. So yeah, which is maybe a bit different than usually presented. So the accuracy of these methods is actually pretty much the same. Battery consumption is the same. And in both approaches, the data can remain in the device until it's voluntarily uploaded. And actually, in my opinion, in both of these approaches, you also share the location data. But the question is, like, who do you share it with? Do you share it with the health authorities or random third parties that install hardware or run dicey apps? So here's an kind of an example. So this is a contact tracing map from South Korea, where they have an approach where this data is kind of transparently published, and kind of my view is that all of these approaches that are now proposed actually do publish this map. It's just like, do they do it in a controlled manner, or do they just leak this data to some random parties is kind of the main difference. Okay, so this is the final slide. I'm running a bit late. So what I would like to kind of conclude here is that it seems that this Bluetooth was kind of selected as the main method or method that should be used instead of location data before this value proposition of how private it was ever tested. And it seems that it's not really, so it doesn't live up to its promise. So, and as a result, I would kind of like to see a kind of a reset in the public discussion that if the Bluetooth is not as private as it claims, so should we then kind of reconsider location data? Okay, but thanks. That's my main slides.
Okay, thank you. And maybe we can have a very quick question if someone has. So you could either raise your hand or put a question to the chat, or tell in the chat that you want to ask a question. Yes. So my question would be that, so what would you suggest to be the solution to? So if location is not good and BLE is not good, so what should you use?
Well, I'm actually, the thing, my view is that kind of location is also like, you cannot like avoid using this location. You just kind
okay,
of,
so it's always there.
Yeah. But if these apps would instead record the locations and share it with the health authorities, then it would be a lot easier for them to aggregate and anonymize the data before publishing this. So it wouldn't be kind of uncontrollably leaked together with too much personal information. So this would be my suggestion based on what I currently know about this.
Okay.
Bluetooth systems.
But yes, and so thank you, Edi, for the talk, and we can now continue to the next. So let me share my screen. So next speaker is Alexander Tenrud. So he's a leader of FAIA, the Finland's AI accelerator, and also ecosystem and partnership lead at Silo AI, which is the largest private AI lab in the Nordics. And in his talk, Alexander will share a progress update on 2 different projects: the Pulse, an open for all and free to use dashboard now costing the Finnish economy, as well as computer vision tool for physical distancing. And indeed, his talk title is Sharing Light on the Work of the FAIA AI Task Force. So please, you can share the screen now.
All right.
Yes, it's visible. Good.
Great. All right, great to be with you guys. So my name is Alexander. I'm the lead of FAIA, which is short for Finland's AI Accelerator. And just a quick background so you can know kind of what perspective I'm coming from. So FAIA is one of the kind of key initiatives emerging from the national AI strategy, started back in days by Juha Sipilä and his government. And it's nowadays actually a public-private partnership. So we have some initial funding from the Ministry of Economic Affairs and Employment, as well as technology industries, and also Silo AI. So what FAIA basically does is we help Finnish more established organizations to apply AI in various kinds of ways, and also work as an ecosystem player together with Silo AI. So fostering the ecosystem and working as much with different AI companies together, and that way helping also as many as possible. What we did during Easter was that we launched an open call for AI experts to form a task force to fight COVID-19. And during 4 days, we got over 50 experts that applied and came up with different ideas and how they could help. The ideas, of course, varied in very kind of in a big way. So we had a lot of people focus on computer vision and how to leverage computer vision in different ways. Also, kind of how to maybe model the spread of the pandemic and such, and others. But one of the kind of clear things that we decided, and we have an advisory board, was that we should not, because this is an ecosystem initiative, and people are doing it on their either on their work time or their spare time, and kind of working for the greater good, so to say. So we should not compete with any existing solutions and services that are on the market, and also the initiative should help as many as possible, and such be publicly available, everything we do. And what helped us a lot of the task was that we actually got some initial funding from the Centennial Foundation of Technology Industries. The big problem, however, kind of challenge that we witness immediately was that when we launched the AI task force, my phone started to ring quite much, and especially from the kind of public side, the government side, we were asked in several ways how to help with kind of improving the situational awareness so that public decision makers could make the right decision at the right time. If you look back at the different initiatives of how to the government has been able to decide on different kind of helping packages for businesses and such. What we really did here was, okay, we were looking into the kind of what other great initiatives we already had in Finland. So we had, for example, the business school and our graduate school of economics, having the Tilannehuone, and also great ecosystem initiatives such talouskriisi.fi, which had started. So we didn't want to do anything that kind of would anything on our own, but basically help these good and great initiatives succeed even better. So what we did was actually look at, okay, if the government needs this kind of help, probably also just the everyday business person and business decisions makers also need to be able to make the different decisions. And during the crisis, of course, the kind of situational awareness and the different models you have been using are not anymore working. So you need to be able to actually now cast and forecast the economic development to make good decisions. And many of the official statistics that we have here, which are of course great, are updated with a delay. And so we noticed that the thing that we could do as a task force was basically bring different data sources that would be in real time, so that we could actually, the decision maker would not need to wait a month or two for some kind of report that would help them in their own day-to-day activities. So for this, we kind of in 3 weeks we come up with a MVP, if you may. So we launched an online dashboard that compiles real-time economic and financial data. And of course, the goal is to utilize several data sources and thereby help decision makers and companies to better understand the situation they are in at the moment. We call these different kind of tools, we call them pulses, and that's also the website or dashboard we have up and running is pulse.fia.fi. At the moment we have 5, and I will kind of show some light on what these are. And just to make sure that people are having the right expectations, so we are not trying to analyze the figures and graphs the dashboard provides, but this is more like an public available site to support decision making and combine these kind of information with their other source of information. So right now we have the dashboard up and running, and it compiles and visualizes real-time data sources. And as I said, there's 5 of them. So News Pulse collects. I will actually go through that a bit more in depth on the next slide. But that basically collects the news about companies in Finland to kind of be able to spot trends. And SME Pulse follows development of invoicing, trade receivables, accounts payable, as well as payment periods at SME companies. And this is, of course, extremely important because in Finland, roughly 98% of all the existing companies are SMEs or employing 1 to 5 persons. Then we have the unemployment pulse again, seeing how we could be now casting the unemployment rate. I'll also go through that in a few moments. And the 4th is the market pulse, which monitors the industry-specific development of Helsinki stock exchange and then compares it with historical volatility so that we can try to make sense of where the market is going and how are we evaluating the companies. And then the last is the cyclical pulse that is basically tracking traffic volumes and trying to from those kind of extract information of where the Finnish production and the economy as such is going. The news pulse. So I said I will go through this. So this is just basically a screenshot shot from the website itself. Some of the text as you see is in Finnish. I do apologize for that. But the pulse itself tracks news and other live feeds about companies and classifies them into risk levels. And once again, this is of course in real time, so we're following all the bigger news channels in Finland and working on actually getting also the smaller rural newspaper and others on to be included. But what we'll hope to see here is, of course, understand trends and others where we are going. So as you see the line there, the line chart is a 30-day moving average of the risk level. And what we do here is basically, it's built by Samuel Rönnqvist and very much based on actually Turku, on the Turku NLP group work. So we have name entity recognition, that model that is based on Professor Sampo Pyysalo's work, and also the Turku neural partial pipeline to analyze the syntactic, the structure and the morphology of the words. Also based on Turku NLP group. But what we do here is when then we are able to recognize a company, then we kind of take that, use that and see if it is a positive or negative news, and then match it to the kind of industry sector that the company is working on. So this is the way we can actually see how different industries are evolving during the time, and of course this is able to kind of give you some kind of overall view of how the economy is progressing. And regarding the kind of UX is, we have the different risk levels. So risk number 5 is the biggest one. So that would be basically having a company going bankrupt, and risk number 1 then is, for example, words as cut and others. So this is again to get the kind of overall risk feeling and the situational awareness in the economy. Then another example would be the unemployment pulse. So here we kind of took one of an old ancient paper by Google chief economist Valherian from 2009, and also did some of the work that ITLA here in Finland has been doing. So we try to nowcast unemployment based on Google search. Here the Google Trends is basically a aggregated sum of several search keywords regarding Google search that would tackle or include different unemployment words, and then we look at how are the trends moving, and then actually have tried to kind of, then we took on the second graph, the lower one is the daily numbers of Kela's benefit applications and the number of unemployment, the layoff periods that have started. So what you can see quite interestingly here at the Google Trends, actually quite nice matches the Kela, and is of course roughly let's say 7 days before they actually the applications get accepted at Google Kela. So basically you can in that way do some nowcasting and short time forecasting with the Google searches. At least it looks like it. So this is 2 examples of the different pulses. So next steps, and I hope to kind of also, if there's somebody in the audience listening to this that would be interested to do some work in the AI task force, please let me know. But what we are doing now is, of course, if you think about the dashboard as such, we have now the kind of MVP up and running. It's in use, and that means that we have the data infrastructure somewhat in place. So now we can actually focus on different, bring more machine learning to the context, and hopefully be able to do some modeling and forecasting in the future. Also, we will be launching new pulses, for example, changes in consumer behavior, together with Omnicom and Houston Analytics and other pulses as well. And kind of big initiatives here is also having more companies sharing their data for the greater good. Here on the right side of the screen, you actually see a snapshot from a news from last week that the technology industry of Finland started an initiative with kind of to have the companies actually donate their APIs and their data, and this we hope Pulse itself it could be one of the places that we can make this data available and visualized. So the goal for the Pulse.fi is actually to be the de facto dashboard for all real-time data sources regarding economic nowcasting and forecasting. And I think that, of course, now we're in the kind of a distressed situation, and the economy is not in the greatest shape. It's not in the greatest shapes. But then again, I don't think that this kind of Pulse dashboard will lose its magic after even after the COVID-19 crisis is over. So this is an initiative that will also continue in the future. So that was basically the first talk about the pulses, and as said, there are many ways to kind of be involved. So if you have anything you want to kind of ask or be kind of actually helping out, that's one possible. We have several different people with different backgrounds here. So we have AI experts, people with coding skills, but also economists and others. So who are thinking about this bigger picture. And I think I'm actually running out of time here, so I will just give a very kind of short presentation about the other thing that we have been working, Silo AI. So again, here the background here is basically the same. Of course, we need to somehow be able to open up the society, but doing it in a responsible and safe way. So what we have been working now on the previous weeks have been physical or social distancing detector. So basically a computer vision powered platform able to detect different characteristics such as total number of people in the space / room and distance between individuals. And of course, this is meant, the solution is meant for example, for malls and others and public spaces that have, of course, the responsibility to kind of ensure the safety of the citizens. And here's just a picture of how it is. So it's a bird's eye view of distance estimation, distance statistics. So again, it's not a kind of the intent is not to focus on individuals, but kind of the bigger masses, and also to give kind of the a way for malls, etc., to comply and do some compliance regarding the public safety. And of course, when you have this kind of different these kind of AI solutions, which we see now popping up every now and there, every here and there, basically what we need to think about is, of course, the privacy, and the privacy first approach is of course that what we want to see, and that's something we have been real much focusing on here. And what I would because I think we need to leave some room for the questions also. So I will kind of leave you with a short marketing here. So actually, if you're interested in the physical or social distance detector and want to learn more, Silo AI is tomorrow hosting a webinar where we will publicly display and also come up with the tool. So I'm hoping if you have interest to watch that, then you of course just sign up through the Silo website and learn more about that. Thank you.
Okay, and we already have a couple of questions in the chat, so maybe if Pelin, if I read the name right, could speak up and maybe ask the question. Or I can also read the question from the chat.
Well, if you can.
Yes, we can hear you.
You can read it, yep.
Yes, feel free to ask.
Yes, my question was about the data used for the pulse generation. How can you get up-to-date data about invoicing, receivables, and things like this?
Yes, a very good question. So the SME Pulse is actually updated twice a week, so it's not a daily updating Pulse, but it's based on ACCOUNTER data. So they have roughly 25,000 companies that use the ProCounter services, so which is basically running in real time. And what we have done with the data, or ACCOUNTER actually have done the work there, is to use just the average of 10,000 companies. So you can't actually go back and trace any data to any specific company. But so the data that we have there on the SME Pulse is based on aggregate sum of 10,000 companies invoicing.
Okay, thank you. And then we would have a question from Timothy Tan. Do you wish to also speak and ask the question?
Yeah, so my question was basically what features would be most important to look for if we're trying to build a ML model to predict the virus? Like what kind of trends are most important to?
Yeah, that's a very good question, and actually we will continue the discussion with the task force tomorrow. So this, as said, we have a clear goal. So first of all, we set up the dashboard, come up with different data sources, and then look at the different forecasting or nowcasting models. So we have a meeting regarding that tomorrow, which would probably mean that I'm more wiser. The problem, of course, with the models is that it's hard to predict something that is so unstable and unclear as the situation we have at hand. So what I'm most would like to look into is, of course, how to utilize the SME data, but also then as second, how to look deeper in the kind of how consumer behavior is changing. So now we have both data from, let's say, the banks and the use of credit cards, and using that data as one source, then look at maybe combining that with Google searches and Google Trends, and then having checking out how that changes. For example, the 1st of June, when the restaurants again are able to open, and these kind of, so seeing what kind of industries are moving to what direction is the key here. But those two will maybe be my guess of what we will be focusing on. But how, then again, the question of what kind of models and what kind of expertise, that's still unclear for me.
Okay, thank you. And I guess indeed we don't seem to have any more questions right now. So I will share the screen for the next week's schedule. So indeed, we will continue next week. So, well, first of all, thank you to the speakers of today and to the audience as well. And so feel free to join us again on 8th of June. It should be at 3 o'clock. and 15th of June at 2 o'clock. So our AI and data science against COVID-19 seminar will continue. And indeed, you can find more information on the website, which is continuously updated. But thank you once more, and hope to see you next time. Bye.
Bye.